a very simple reaction. That's what I meant to say. So we can start off with something like h squared plus 1/2 O2 equals H2O, and it can be both directions, but we're going to consume one direction because I'm lazy. We're going to consume, so basically what's happening is A plus B is going to C and not transferring back into A. And why is it taking forever for my computer to load that? That should not happen. Anyways, what we can tell from here is that basically there is, right? And we're going to do VH2O equals +1. I think there's a mistake here. There should be a -1 here, I think. And this should be a minus, I believe. And what does that allow us to do? Basically, that allows us to solve everything. I mean, solve a lot, but not everything. Yeah, yeah. Now that is basically how we get um, reaction with CA and CB. Yeah. So yeah, that's how you do it. If you're doing a 0D version, you would just do this equation over here, which is basically R equal KCA CB, where CaCb is molar concentration, and then the K is the rate H2R, I believe. And there's going to be molar rate in oxygen equals to -1/2 WOI-R. Molar H of H2O equals plus omega, no, M of H2OR. And then these things you use to solve it, basically. I think taught me this. I think it was UIJ, and then if it was and then it would be plus PI, I believe, double dot like that. And then it's the energy equation over here, rho E plus PUJ. I will explain this later, but it's rho KUI equal rho T. I think it's actually rho I. I think I made a mistake here. I think it's rho I, or maybe it was another. I don't remember. But it was definitely a professor that taught this. Not so much to me. It was tau IJ over here. IJ UJ minus Q, which is Fourier's law, which is going to be. Let me check. we used J over here, so this should be I think I was supposed to use I over here, so that makes more sense. I'm checking that the energy equation is a scalar. If it's not a scalar, I fucked up and I need to redo the whole thing because energy is always a scalar. If it's not a scalar, then there's a mess up with the whole thing, and you need to double check the whole thing. And it's going to be 0, 0, and it's going to be negative summation of hi omega dot k, and it's going to be omega dot k like this, and this is our um, Navier-Stokes into a matrix block form. This is called block matrices, I believe, because these are bigger matrices and smaller matrices, but I'm mixing terms because this is obviously not correct because this is this is not in index notation, so I don't know why in my notes I have it like that. Yeah. So again, that's beautiful and all, but I should really be explaining all the concepts first before I can go there. So let's go start with the chemical. No, not chemical. Let's go with the species diffusion, which is over here, I think. No, we should really start with the should be in everyone's head, right? When we talk about fluid mechanics, and it is obviously the one equation that I have memorized because I have used it so many times that if I haven't memorized it, I think I would have what's the word? I don't know. And then I already forgot the gravity term. Which the reason I keep on forgetting the gravity term is that it's going to be inside the pressure. So it's going to be rho g or rho f, the body force. It's going to be a vector, not a matrix. No, let me think. It's going to be plus gradient that tau. So I'm mixing up notations here, which is bad. I mean, it's fine on my part, honestly. The reason I know it's kind of fun when you keep on doing different notation because it's getting on my feet, anyways. So as you know, this is the acceleration term. This is the convective term. This is acceleration. The acceleration term, convective term. This is the pressure term. This is the body force. This is the shear force, shear kind of thing. And this tau is defined by saying ij. This equals, I believe, let me just remember, vi xj plus rho vj rho xi. And that is our mu over here. And it's going to be plus, I believe, the bulk viscosity plus 2 divided by 3 viscosity identity, which I should be using and my tablet's frozen again. So that is fun. Let me just wait a few minutes for the tablet to. Is my voice actually responding well? I'm not sure. I haven't been charging my battery's low, so it's not really charging. I guess it's going to be a bad video then. Let me just charge a little bit over here so it actually has some kind of quality check. Because when my battery's low, it doesn't really do the video that well. Over here, it's going to be rho ij, and it's going to be gradient dot v. And this term is why this thing goes to 0, as we all know. That is true. As you may have known already. Anyways, no, this goes to 0 if it's incompressible, by the way. For compressible, which we're dealing with, this is in play. So next we're going to do a species transport equation, as I've talked about. It's going to be, I believe, rho. Oh, this is wrong again. So let me get this right. So again, we're talking about species. So we're starting with rho yk, which I'll explain what yk is. There's actually a polar form of this if you didn't know. So this is mass of species k per unit volume. Is over here. Is in the middle. So this over here is equivalent to say the mass of species k per unit volume. To the more full extent, it's going to be considered the full, thing. And then we're gonna have this diffusion equation, which we all know from Navier-Stokes that there was already going to be a combination of diffusion and convection and other PDs solve Reple-Sohn equations sometimes and so on and so forth, depending on what kind of application you're using it. So we're going to start from here, and what must always hold is that basically n